So for problem 6 on our test, we have to prove a lemma to find linear independency for basis vectors. And to do so, we will have for a set T containing vectors A, B, and C, D for all A, B, C, and D elements of the real. And by lesson 2, we learned about systems of equations and linear combinations. And so using those, we will have, using those for on our 2 arbitrary vectors, we'll have x times AB over plus y times CD, which equals 0. And using our system of equations, we come up with these 2 equations, and we start by solving for y in our first equation. So we take our yc and we subtract it from one side, which can be rewritten, and then we have our c, which is divided and brought over to the other side, and thus we have y equaling negative x a over c. If we take this and plug it into our second equation, we'll end up with xb plus negative xa over c times d, which equals 0. If we distribute the negative, we will end up with xb minus xad over c, which we can add to both sides, bring it on the other side of the equation. And here we cancel out our x's by dividing them on each side. So we're left with b equals ad over c. With this equation, we can subtract cb to the other side, and with this we can state that 0 equals ad minus bc, which is equal to linear dependency. And on the reverse, ad minus bc does not equal 0, shows us linear independency. And to kind of get a better understanding of how this might work, the equation we passed through earlier, if we take any non-zero real numbers and we plug them into our x's, and it is equal to 0, then it shows that we have a linear dependency.
So now that we've proved our lemma, the actual proof for question number 6, let V equal the space R2 and T be a set consisting of 2 vectors A, B, and C, D, such that A, B, C, and D are elements of the real numbers. The set T is a linearly independent set if XA plus YC equals 0 and XB plus YD equals 0, and the only solutions for X and Y are equal 0. By the lemma we proved earlier, the vectors A, B, and C, D are linearly independent if AD minus BC does not equal 0. Since T is a linearly independent set and the dimension of V, R2, equals 2, and the cardinality of set T also equals 2, and T is a subset of V, then T is a basis for set V, or equivocally, T is a basis for a basis set for R2. So now, in reverse, applying our condition to vectors that we already know are basis vectors. So we have the standard basis vectors 0, 1, and 1, 0. So we apply our condition, we have A times D, so 0 times 0 equals 0, and then 1 times 1, which equals 1, and obviously 0 minus 1 is negative 1. So since this does not equal 0, we know that we have 2 linearly independent vectors that span R2. And then, so now we have vectors that aren't the standard basis vectors. So if we apply the same condition, A times D, so negative 7 times 1 equals negative 7, and then C times B, 3 times negative 4, which gives us negative 12. Negative 7 minus negative 12 equals 5, which is also non-zero. And we know that predetermined that this is a basis vector. These are basis vectors, and they're linear independent, and they span all of R2.